Have you ever wondered how electricity got to your socket? Like when you plug something inside here, you press on, suddenly got electricity. How did electricity even get here in the first place? That is our main question for today. And a very important device will be the one that will help us to know how we get electricity in our house. So you take a look at this big picture. This is the whole plant, okay? You have a power plant. That's where electricity will be generated, either through, I don't know, burning coal, which is not great, or hydro, or solar. I don't know, solar is not very big yet, but hydro is okay. Whatever method, as long as you generate electricity here. Typically, AC is generated from moving turbines, steam, or moving water turbines, or something that is moving. That's how we generate AC. So when you generate that AC, you need to send it a very, very long distance because power plants are not everywhere. They only exist in certain areas in your country or in your housing area or in your state. So when you have a long distance transmission, we need to change the voltage. You see, from 12,000 volts, need to convert to 240,000 volts and then send over power lines. If you look around outside your house, you might see some of these power lines there, especially if you are not quite near the center of the city. If you're further away at the edge, you would see these huge towers by the highway, by the roadside. Okay, so this is our long distance transmission. You see this zigzag? It means over a very long distance, many, many kilometers later. Then you come to a housing area. You can't just send 240,000 volts into a housing area. You need to step it down. So you need some kind of way to reduce the voltage from 240 kilovolts down to only 7,200. And then you send it over local lines. These are the local lines. Then it goes to your house or apartment. Go inside your house. But this is a bit too big. We need to step it down some more. So by the time it reaches your house, average consumer level is about 240 volts here in Malaysia. Sometimes it changes a little bit, but roughly about there. So you see all this change in voltage, right? How do we do that? From 12,000 to 240,000. Oh my, step down to 7,200, and then finally down to 240 volts. But that's not the end. Still got some more. Inside your house, you have the socket I showed you just now, right? If you want to plug your phone charger in, you cannot just throw it 240 volts. It's going to burn. So if you look at any of your chargers that we looked at in the earlier theory video, you will see some kind of change in voltage right there. So here I have a nice Samsung travel adapter. If you look very closely at your own phone charger, you'll notice some kind of input and output voltage right here. And it's different. So go check it out and you can see, actually 240 volt is just a socket in your house. Every single device, okay, this is a socket in Malaysia, is 3-pin socket with a switch. Every single device, whether it's your phone charger, whether it's your, what do you call this? Power brick converter for your laptop or your TV or something like that, you will also see some kind of conversion here on this side. See the input? 100 to 240. Output, very small only, 9 volts. So you need to step it down and convert to DC, whatever that is. So these power bricks will continue to change the voltage for you. Okay, let me get all these wires out of the way. Excuse me, shoo. Alright. Go look at all the devices in your house, right? So, furthermore, from your house, any device need to convert some more. Maybe 5 volt, maybe 9 volt for a laptop, maybe for your, I don't know, what other appliance in your house, your TV need to change to 12 volts. There's a lot of changing voltage. And how do we do that? The idea is transformer. Transformer is the main equipment or the main tool that will be used to change all these AC currents. Okay, so transformer can be huge, like it could be a whole building, could be a huge machine kind of thing, or it could be as tiny as your finger, your thumb. It's the size of your thumb, these tiny things. And this one you can find in circuit boards, in computers, in speakers, in all kind of thing lah. But these are very, very small. So got small transformer, got big transformer, small, big, small, big. Okay, so how do transformers work? We have learned before in a previous video about this thing called mutual inductance. What happens when you send alternating current through a coil, a solenoid. Now, if it's just a DC current in one direction, you will have a magnetic field created like that. But then if you do AC, the flux keep on changing and then it will affect a second coil because of this changing flux. This is Lenz and Faraday's law put together. Okay, so one coil got electricity. Another coil will have induced current inside there. Okay, so that is what we call mutual inductance. One coil's magnetic flux that is changing affects a second coil. That is the whole idea of a transformer. So let's recap that a bit first. Transformers. So when alternating current flows in the primary coil, alternating, the current keep changing direction, but let's say it's flowing this way for this moment in time. Okay, when it flows, it causes a changing magnetic flux. Magnetic flux is what? I go review a bit. Magnetic flux in the primary coil. And also, don't forget the soft iron core. So right there, and the soft iron core. Okay, so you want to think of it, how does it look like? Well, in solenoids, the field are roughly like this. But the iron core, what's the purpose of iron core? Actually to guide the magnetic flux, make it stronger, so that it can link together with this secondary coil. Okay, so maybe for this particular current, the magnetic field will look like this at this moment in time. Next moment, it changed direction already. So something like this. So it will guide a lot of this flux to link together these two coils. So that's your B. And this is also changing every time the current change direction. Okay, so we have flux in the primary coil, but also the iron core. Now, how about the phase? Well, one thing you want to mention is the changing magnetic flux. This flux is in phase. In phase with the input current. So on the left side. Let's put that there. Okay, so why is this true? Because you see, the flux depends on B. Phi equals to BA. And we also know that the magnetic field is generated when there's a current. So therefore, flux is proportional to current. So if your current is changing like this, I against T, that means your flux is also changing with the same phase. Phi against T. Okay, so flux or magnetic field lah. Flux density. There we go. So in phase together. Alright. What else? So how does that affect the secondary coil? Usually you need to explain that, right? In the induction. How does this changing flux affect the secondary coil? Does the secondary coil like change in flux? No, coils do not like a changing magnetic flux. It will do all it can to oppose the change. So let us look at the next part. So since the primary and secondary coils are linked, what does it mean? Magnetic flux linkage. There's a reason why we call that magnetic flux linkage. So N phi. Linked, okay, the magnetic flux kind of curls over and also goes through the secondary coil. Because they are linked. That is the word you want to use. So, if they are linked, how is the secondary coil affected? When they are linked, that means there's also a changing magnetic flux. Changing magnetic flux in the secondary coil. On the right side. And this change is in phase with current. In phase with current. This is from Faraday's law. Remember Faraday's law? An EMF or current will be induced, let's use orange color, depending on the change in flux. Where is the change in flux? They both have the same change in flux because they are linked. So what does it mean to be linked? Linked means the flux through the primary coil, I'm use P, is the same as the flux through the secondary coil. Because they're linked together, you got change, I got change lor. So now the EMF induced in the secondary coil will depend on the change in flux. Or, since flux is related to current in the primary coil, then we can say that, oh, so actually the secondary coil's EMF is proportional to the change in current of the primary coil. That's what we're saying in the sentence just now. Okay, moving on. Okay, so now we talk about whose law was this? We just wrote up here. Whose law is this? Faraday's law. So we're going to say, oh, from Faraday's law. So what is induced? When there's a changing flux, this induces an EMF in the secondary coil. So that's the ES that we have in the top right corner up there. Okay, so now we have, see, primary coil generate changing flux. Secondary coil, what got changed? Induce current to oppose a change. Okay, so then you have a current now flowing inside here. So depending on how you arrange it, your output can be positive, negative, or vice versa. But just know that there's a changing flux. You're going to oppose a change. So something like this maybe. Current. Right? Now the next part will require you to remember a little bit of your induction. Okay, so we have induced EMF in the secondary coil. And that's equal to the rates of change of magnetic flux in the secondary coil, comma. Remember, this one is EMF in the secondary is proportional or equal to the rate of change of flux. What does that tell us about the phase? So because of this Faraday's law that we just mentioned, so rate of change of magnetic flux in the secondary coil is out of phase. Out of phase with who? Out of phase with magnetic flux. Magnetic flux where? In secondary coil. In short form, we are saying, we are comparing d phi dt, the rate of change of flux versus just phi. Now these two is a derivative. d phi dt is a derivative of phi. So they will be out of phase 90 degrees. Miss, why? Okay, let's draw a graph. Come, we draw a graph. So let's say we have a graph here, something against time, and I want to draw the flux through the secondary coil. So maybe I assume, okay, let's say it's a sine wave. Okay, sure. So sine wave like this. So this is how the flux is changing. Now remember, the flux in the primary is the same as flux in secondary, so don't care which one, the flux is changing. That's all that matters. So then comes along Faraday's law and says, oh hey, the EMF induced is actually negative d phi dt. This is called the rate of change of flux. How does that look like? Well, we could draw some graphs and figure out, okay, how to find the rate d phi dt from this graph. D phi dt also means the gradient of the phi t graph. So we need to plot a graph of the gradient. Okay, so at the maximum point, let's look at this one. What's the gradient up here? 0, flat. So no EMF induced, no rate of change of flux. So kind of put an X here to mark my spot. Oh, we forgot about the beginning. Okay, let's do beginning. So beginning here is a positive gradient, increasing. Okay, the function phi is increasing, but we want to negative d phi dt. Okay, if you want to do that, then you must have a negative value for the gradient. We're talking about the gradient. Next, oh, you here got one more point. This one. The gradient is negative, is sloping downwards. So I'm going to put a positive value as my rate of change. Next one. Down here. This one, got gradient or not? No, coil is flat. Is there a rate of change? 0. Okay, so 0. I put X here. Last one. This place, the graph is increasing, got a positive gradient, so I'm going to put it at the negative side. So whether or not you have the negative, you will still be out of phase. There's no way it can be in phase. So if I plot out this graph of induced EMF, I'm going to use a nice deep purple, I would get a cosine graph that looks something like this. So this graph is my d phi dt graph or my induced EMF in the secondary coil. And there's always a phase difference between them. There's no way they're in phase. Okay, so if I take my reference point as this point, you see it's 290 out of phase. That is comparing between phi, okay, the blue color one is phi, flux, and the rate of change of flux. Always out of phase. So just need to know, if you can't remember it's 90 never mind, just know it's out of phase. This is the important one. Out of phase. Okay, so we talked about the phase already. Hence, let's continue the story. We can also say that the induced EMF, we plot the EMF, right? d phi dt is the EMF. So hence the induced EMF is out of phase with the flux or input current. Because flux is proportional to the primary input current. That's the very first graph we draw up there. So I scroll up again. This one. Input current and flux in phase. So we come down to here. Flux in phase with current. So flux or current, the graph will be this pattern. And then you have the induced EMF or the rate of change, which is out of phase with that. So make sure you know how to draw this graph, how to think about it when you come to induction, because this is a very important idea, rate of change of flux. Okay, last one, Lenz's law. All right, let's talk about Lenz's law. So from Lenz's law, the induced EMF, which is ES, if you want to call it there, EMF in the secondary coil, is in phase or out of phase? Out of phase, so we can say out of phase to the primary coil to oppose the change. Now this, the main idea is just oppose the change lah. Okay, so if we draw space here lah. If I say the primary coil, the flux, the EMF, okay, this is now an EMF graph. The primary coil EMF looks like this. This is E for the primary. Then the E secondary will be out of phase. So completely opposite. E secondary. How I know that? Because of Lenz's law. So we know they will oppose a change. So EMF will be opposite. So that's a kind of a quick recap of what mutual inductance is when you think of rate of change of flux and induction between two coils, how they are linked and how they affect each other. But how do we apply this idea to transformer? We want to convert voltage, right? How do you link these two ideas? Yes, we know there's mutual inductance, but how do we link them? Here's the magic. We have talked about flux, but have we talked about flux linkage? Ooh. So people have found out that they can change the input voltage and the induced EMF depending on the number of coils, the number of turns. N is the number of turn of coil. So you see this on the left, very few N turn, right? The right side, wow, so many turns, 32 turns. And what happened to their voltage? One is 120, one is 240. Is there an equation for this? Yes, there is. Let's look at the equation, how to derive that. So first one, let's look at the primary coil, which is on the left side. So primary coil, what is the EMF or voltage across it? We know the voltage is going to be, what d phi dt. Oh, got flux flowing through the thing, right? Now I draw flux. I put dotted line to remind you there's flux changing. Whether in the primary or secondary, I don't care. There's flux changing. That's all we need to know. There's flux changing inside here. D phi dt. So in the primary, there will be a d phi dt in the whatever the flux change in the primary is. But don't forget the negative, and don't forget one more important thing. Last time we say magnetic flux linkage. This is N phi, magnetic flux linkage. How many turns times the flux? And the real thing is magnetic flux linkage. So that's why you must include the number of turns as well. So this will be N P. So the voltage that is on a primary coil is due to a flux change in primary coil times the number of turns. Well, how about an equation for the secondary coil? Okay, let's do one more. So secondary coil, whatever voltage is generated or measured across the sides is equal to the negative times magnetic flux linkage or rate of change of magnetic flux linkage. So don't forget, actually there's a NS. Now we want to make sure we count the NS because it will matter because we're trying to do step up and step down. So we can have, d phi of secondary over dt. So that's for our primary and our secondary. So how do you relate both of these? Just now we said that both coils are linked by a magnetic flux. Okay, number of turns is different, but the flux is the same. So we can write here, since both coils are linked, then we can say that the flux of S is same as the flux of P, which is just the same throughout the whole thing. So you can also conclude and say, therefore, d phi dt of S is the same as d phi dt of P. Same flux, same rate of change, they are linked ma. They experience the flux together. So from here, we can come up with a ratio already. We're like, so the phi and phi is the same lah. This component is the same as this component. So you can equate them. So you can come up with a ratio actually. This ratio is saying, since both have equal rate of change of flux, I can do a simple ratio of their V and their N. So what we have here will be Vp over Np equals to, what's the other side? Vs over Ns. That is kind of putting together equation 1 and equation 2, knowing that their d phi dt is the same. So you equate d phi dt lor. Okay, so from the step down there, I go to the next step. So this one, go up here, equate their d phi dt. Then you get this ratio. Okay, more commonly you will see it written as the rate. They'll put all the V on one side because usually you want to find the secondary coil and secondary coil's voltage ma. So usually we will write it out in this way. We will say that, I'm just going to write in one color. Too many color to change now. You get the idea lah, huh? So we already say that Vs over Vp equals to, the other side, Ns over Np. This is the equation you want to remember, the ratio of how you can step up and step down the voltage just by the number of coils. One side you wrap more, then your voltage is higher already lor. So to see in action, you can play with this. Reduce the number of coil. Wow, you see drop until 150. Drop some more. Drop until 52 liao. And you can also see how their alternating voltage can vary. Blue color is input, primary. Pink color is secondary. So depending on the number of turns, you can just change the voltage however you like. Just wind more lah, wind more. Then you can ratio and change voltage. I want 45 volt, you change. I want 200, you change. Up to you. You can just really do a lot of flexible thing. Okay, so that is the beauty of transformer. When you have a peak input, 120 volts, depending on how much windings you have, number of turns of coils, you can very easily change your output and input. Okay, go play around with this simulation down in the link below. I think this fella did a really good job creating this transformer simulation. Now, one final thing to note is that if we want to look at the ideal transformer, then there's no energy loss when you're converting from 120 volts to 240 volts, for example, in this case. But what does the ideal transformer mean again? How to note? So this is a side note. For an ideal transformer, what does that mean? An ideal transformer means there is no energy loss when you are doing a step up or a step down. Step up to higher voltage or step down to lower voltage. No energy loss. So you could say that their power of input is the same as the power output in the secondary coil. Okay, we have done some examples for this in the previous section already, but just a reminder of how you can think of it lah. Alright, so power input is what? You got a current, PIV, right? Primary coil equals to output, a IV of secondary coil. This is only for ideal transformer. No energy loss. So I'll make a note. This means no energy loss. Efficiency 100%. My head is blocking a bit, but never mind. Let me finish writing first. Okay, 100% efficiency. There we go. But in real life, does this exist? No, sadly no. We always have energy losses. All these darn eddy currents and heat losses and resistive stuff. So it's good to also know some of these because once in a while they can ask you in past years. So yes, ideal transformer, no energy loss, but actually got some loss lah. So some of the problems, we can address them by this way. So how do you make sure you have the best, highest efficiency possible? Both coils, firstly, you are insulated, so the coils can be wound tightly without any short circuit. What does it mean by wound tightly? Then usually you have all the copper coils wound into a solenoid, right? Have you ever wondered, those copper coils touch together won't short together, meh? Where's a picture of it? I have some. These fellas. You see all these? They touch each other, they won't short, meh? No? Actually, this one got insulation one. Got a layer outside so that even if they touch together, they won't short circuit. Electricity cannot jump from one winding to another winding. It's insulated. That's what it means. Okay. And there's another problem we want to address called magnetic flux leakage. So the way to reduce it is to make sure you wound the coil on top of each other. So wound on top of each other to reduce magnetic flux leakage. What does it mean by magnetic flux leakage? I don't have a nice diagram of that. Don't really have a nice diagram. Here, I can draw it here. I draw it here. So most of the flux will be linked over to the second coil, but there can be some flux that will just come out there. Then all this, what are you going to do with this wasted energy? Some of this flux leak out of the coil. So that's a problem. And usually you won't see people use this kind of layout. They will put it much, much closer on top of each other almost. Like this one, you can't really see both coils are on top of each other. Or like this one, what they could do is they wind the second coil on top of the first one. So there's overlap, no leaking. Flux is fully linking both coils. Okay, so make sure they wound on top of each other lah. That's one thing. Okay, what other problems do we have that decrease efficiency? The next thing is a problem of resistive heating. These wires got big current flowing through them. Okay, a current flowing will make the wire hot. That's why in experiments you say don't touch the coils, they are hot. So make sure when you design a transformer, the coils, you try to make it with materials with low resistivity like copper or even better, new element. Why? To decrease what we call resistive heating. When the wire get hot, you lose energy, thermal energy loss. That we don't want any energy loss. We want to keep all the energy, electrical energy converted nicely from primary over to secondary coil. So that's one problem. We solve it with using wire of low resistivity. What else? Flux leakage. Soft iron core. We see this soft iron core so many times. Actually, what is it for? The soft iron core that you always see in transformers or coils is used. Why? Because it magnetizes and demagnetizes very quickly. Magnetizes and demagnetizes quickly or very easily. And what does that do? So it decreases heat loss. Why cannot use other material? Well, because those they might store the magnetization. Then you have all kind of problem with the magnetic field. It's not a clean, nice linkage. But also the soft iron core the main purpose is to enhance the magnetic flux. So if you look at this picture right here, these are called air core coils. It's just air only lah. So you create some kind of magnetic field in air. But only one part of this flux will go over to the secondary pole and link together. But once you put some kind of iron core wrap around, the iron core will guide the magnetic flux. Make sure there's very close linking. Most of the flux will in there. I mean, there'll be some leakage out lah. But most will be inside this magnetic flux, inside this iron core, linking together both. So that's the purpose. It enhances and guides the magnetic flux to go in a certain direction inside it lah. Okay, so this iron core will also become magnetized. It will also become a magnet. Magnetize and demagnetize easily ma, so it help guide lor. Say, hey friend, come this way. But there's also another problem. The iron core is a piece of conductor. So you have another problem if you put iron core. You have what we call eddy currents. Wow, how does eddy current look like? Okay. So think of it this way. When you have a magnetic flux changing in the conductor, does the conductor like that? Not exactly. It's also a conductor. So it will try to oppose a change by creating its own eddy currents. So eddy currents is going to look maybe something like this. And there's lots of them inside here, everywhere. Eddy current to oppose the change. Okay, these are what we call eddy currents induced inside the core to oppose the change. And we don't want that. I mean, there are small amounts of them, but we still don't want those eddy currents in there. So what we do is we laminate your iron core. So instead of one chunk of metal, we laminate, we split it up into tiny little loops. That way, current cannot easily say, hey, I want to go like that. Cannot, because you are limited to one single slice. So you have really tiny current in maybe a single slice. See, you can barely see the little orange arrow I draw. So instead of a huge current like that, nope, you can't do that anymore. You can't cross the slices. It's laminated. So all the eddy current is minimized, made very small. They're not removed, they'll still be there, but they're minimized. And this is how lamination works. Solid core, big current flow everywhere, anywhere they want to flow. Laminated already, they can only flow within their section or within their slice. So this will reduce the effect of eddy current, and your iron core won't get hot so much lah. Okay, big current means got a lot of heat, get very hot. Now the eddy current very small already, not so much heating, not so much energy loss. So that's number 2. We do a soft iron core that is laminated. Why do we do that? To decrease eddy currents. Decrease eddy currents. And what does that do? Reducing heat loss. Wow, what is up with my handwriting tonight? Reducing heat or thermal energy lost. So these are all the problems that sometimes past year can ask you. And sometimes they may ask you why you do a certain things, why you laminate, or you must know the reason. Okay. Now, final thing before we close the video is advantages of AC. You have already seen in the previous video when Miss Lee talked about the battle between Edison and Nikola Tesla. They are deciding, when they were designing the power grid, should we use AC or DC to send electricity to houses? They argue, and they decided, okay lah, AC is the way to go. Why is that AC the way to go? Let's just summarize some of the points. You have seen this in the previous example from the previous section, but let's just summarize again. Why high voltage? High voltage because if you want to, for the same power transmission, P equals to IV. For the same power, if say comparing high voltage versus low voltage, if you have a high voltage, means you have a low current. That's good. Why? Because current causes heating. When there's current, there's heating in your conductor. We just don't want any energy loss. So for the same power, high V means a small current, small I. Hence, what? What does that? What's the advantage? Hence, less heating or energy loss, thermal energy loss in your cables and coils. Because you need to transmit over a far distance, right? Has heating in cables. So that means the efficiency is higher lah. When you're going from one place to another, you step up, step down. So when over long distances, this is very important. So efficiency is quite high. Okay, the main problem, heating in cables. Okay, so why do we do AC? This one you already saw in the argument in the previous section. Why do we AC and not DC? First one is because you can very easily change the voltage. You just change the coil, change how many coil, then you can change the voltage. So it's very easy to change the output voltage. Okay, so no matter where you are transmitting, to a house, to a factory, maybe for your phone charger, for your laptop, you just change to suit your appliance. Different appliance need different thing. Different places, factory versus a home, need different voltage. You can very easily change it. The second thing is, when you want to change this thing, you can only use transformers. And transformers can only work with AC. Because you need that change in flux, the alternating current, to induce an EMF. If it's DC, you cannot do this step up, step down so easily. So that's a problem. Transformer only can work with AC, so AC lah, of course, use AC. What else? Generators in the beginning already produce AC. Generators produce AC. The rotating coil that we looked at in the previous section will naturally just generate an AC for you. So just use the AC lah. Generator already produce AC ma. And lastly, this one we will learn in the next section. It's easier to convert or to rectify. That's the word we use, rectify, if you're converting AC to DC current. Much easier compared to than to invert DC to AC. And I mentioned this in the previous section, previous example video. I tried to convert DC to AC in a school project. It did not go as well as I hoped it would, but I did pass the thing. So when you have AC, ding dong diang, it's not great for appliances when you're making circuits. You don't want DC, you don't want AC all the time. It's a bit hard to plan for things. So what we do is we rectify it. That's coming in the next section right after this. So rectify it, then you just have a steady 0.2 amp. You just 0.2 all the way lah. So this one is good. We can do this pretty easily, which we will learn soon. But it's very hard to go in the opposite direction and convert DC to AC. It's just very hard to get something to oscillate properly without killing the whole system. Okay? So keep this in mind when you're learning about transformers. Lots of info today in this video, but a recap of induction and how we add a little bit more understanding of how you can step up and step down your voltage, your output voltage, depending on the number of coils. So that is all for this video. I will see you in the examples video and in the next section where we'll look at how to convert AC to DC. See you in the examples video. That's all for this one.